Hi there, Mr. Sutton here, bringing you the AB Calculus 2-7 Extra Practice Number 1 solutions on Intermediate Value Theorem. For this problem, we're given the table of a cubic polynomial function called h, and we're told that two of the zeros are listed in the table. So that would be at x equals 1 and also x equals -2. They get y values of 0. Between which two values of x does the intermediate value theorem guarantee a third value of x exists, such that the function is 0? Explain your reasoning. So if we're using IVT, right away we check for continuity. Since we're dealing with a polynomial here, we know polynomials are continuous everywhere, so we've got continuity on whatever interval that we could possibly want. Next, we have to check to see if the y value 0 is between any of the y values listed in this table. So we're looking essentially for a sign change, because in order to pass through 0, we have to go negative to positive or vice versa. And we see that there is a sign change. Let's see, not a sign change there. That's not really a sign change. There's a sign change here, though, from -4 to 18. So because the y value 0 is between the y values -4 and 18, the IVT guarantees we have our third x value on the interval from 2 to 4, where we get a y value of 0 for that. On this problem, we're trying to explain why the intermediate value theorem guarantees the existence of a 0 for this function on the interval from 1 to 2. So to use IVT, we need to establish two things. First off, we need the function to be continuous. Now this is a polynomial, so automatically we know it's continuous based off of that fact. It's just known to be continuous. We also have to establish that the magic value, the magic y value we're looking for, is between the starting and the ending y values of the function. So we basically have to figure out if 0, the thing we're looking for, is between f of 1 and f of 2. Well, f of 1, if I plug 1 into this whole function, that's going to be 1/16 minus 1, which is, let's see, negative 15/16 plus 3. Well, 3 is 48/16, so overall that's going to be, what, 33/16, or 2 and 1/16, if we want a mixed number. Probably easier to write it that way. And now if we plug 2 into all of this, it should hopefully be a little bit easier. 2 to the 4th is 16, cancels this 1/16, so that's just 1, minus 8 is -7, plus 3 is -4, and is 0 between -4 and 2 and a 16th? It sure is. Therefore, now that we've established that, we see that the IVT does apply here. There is a 0 for this function on this interval. For this one, we're trying to explain why the IVT guarantees the existence of a 0 for this function on the interval 0 to 1. So to start with, we have to establish that we have continuity for the IVT to do anything useful. This is a polynomial, so we're guaranteed that it is continuous. Next, we have to show that the y value we're looking for, which is 0 in this case, is between the starting and ending y values of the function. So in this case, we have to show that 0 is between f of the first endpoint, f of 0, and f of 1. f of 0 is pretty easy on this one. That zeroes out anything with an x, and we just get -2. f of 1, that's going to be, let's see, 1 plus 3 is 4, minus 2 is 2. And 0 is indeed between -2 and +2. Therefore, the IVT guarantees that there is a 0 on this interval. On this one, we're trying to explain why the IVT guarantees the existence of a 0 on the interval 0 to pi for this weird polynomial trig function. In order for the IVT to guarantee anything, we have to establish that our function is continuous on the interval in question. X squared and x, those are continuous everywhere. So is cosine. All of these functions are continuous, so therefore the whole function, adding and subtracting them, is also going to be continuous. Next, we have to show that the value we're looking for, 0 in this case, falls between the beginning and ending y values. So we need to figure out f of 0 and f of pi and make sure that the value 0 is between whatever we get. Let's start with f of 0. That zeroes out these x's, and then we have negative cosine of 0. Well, cosine of 0 by itself is 1, so that's going to be -1. Next, we're going to figure out pi, if we plug that in. So that's pi squared minus pi, And then let's see, cosine of pi is -1, but we're subtracting that, so we're actually adding 1. So we've got pi squared minus pi plus 1. And again, we're trying to establish that 0 falls between these numbers. Well, this first thing is negative. How about the signage on f of pi here? Well, pi squared minus pi, that's definitely going to come out positive because pi is a number bigger than 1. And if you're adding 1, you're just making it more positive. So this is definitely, I don't really know exactly what value it is, but it's definitely a positive number. So then we can say negative 1 is less than 0 is less than this stuff, which establishes that the IVT guarantees a 0 on the interval 0 to pi for this function. Basically, if you're starting here and you're ending up here and you're continuous, you've got to go through 0 to get negative to positive in that fashion. So there we go. On this problem, we're trying to explain why the IVT guarantees the existence of a 0 for f of x here on the interval from 1 to 3. And we're allowed to use the calculator, which is going to be kind of helpful. Before we can do anything with IVT, we have to establish that we have a continuous function, and there's a lot of places this function could go wrong. So one way you could try doing this is to actually graph the function out. So let's go ahead and do that. So here's my crazy function, and for the interval, I'm going to use 1 to 3. That's all I care about. So let me set that for my window, and then do zoom 0, zoom fit, and hope for the best on this one. All right, so here's my function. And it doesn't look like there's any discontinuities on this interval. I mean, there's definitely no asymptotes to worry about. One thing we do have to worry about, possibly there might be some holes that are hidden on this graph. So this is not a rigorous proof that we're continuous, but it's an indication that we probably are. But let's do a little more analysis just to make sure. So because these are not functions that are known to be continuous, the way you can show they're continuous is by pointing out discontinuities and showing that this interval doesn't have those. So one major discontinuity is with this 4 over x term, we run the risk of dividing by 0. Specifically, if x equals 0, we've got a vertical asymptote. The good news is 0 is outside the interval from 1 to 3. So that discontinuity is irrelevant because it's not on the interval that we're looking at. This next term also has issues. This tangent term, whenever you take the tangent of pi over 2 or 3 pi over 2 or any angles that are basically at the top or the bottom of the unit circle, you're going to end up with a vertical slope, which basically means you have an undefined tangent at those spots. But now taking a look at the values we're plugging in, the lowest we're going here is 1, so that would be the tangent of just pi over 8. And then we're going up to 3 pi over 8. Well, 1 pi over 8 and 3 pi over 8, that whole interval is in between those asymptotic values at negative pi over 2 and pi over 2. So our tan is going to exist on the interval that we're going to get by plugging in this number. So basically, we are continuous on this interval. All right, with that in mind, let's go ahead now and make sure that the value we're looking for, namely 0, falls between f of 1 and f of 3. So let's plug those in the calculator. And again, let me just officially write out we are continuous on the interval. There we go. So to plug these in our function, I've already got this function stored conveniently in my y1. So I'm just going to do alpha trace and pull up y1 and plug 1 into that. And press enter. About negative 3.5859, or 57 rather, 58. There we go. Get it right on the third try. And now let me yank that input from before and just plug 3 in there. Gives me 1.0809. Okay, so we were looking for 0. 0 is between these two numbers for sure. That should actually say f of 3 there. There we go. So yeah, 0 is between these numbers. There's no way to get from a negative to a positive without going through 0 if you have a continuous function. So therefore, the IVT establishes that there is a 0 on this interval for this function. On this one, we want to know if the IVT shows the existence of a c such that f of c equals the specified value. So basically, we're asking, does the IVT guarantee there's a y value of 11 on the interval from 0 to 5 of this function here? We need to establish two things to prove that this is the case, or see if it is. First off, we need a continuous function, at least on the interval in question. We have a polynomial that's continuous everywhere and known to be so we've got continuity established. Next, we have to show that the c value we're looking for, or rather the f of c value, 11, falls between the starting and ending y values on this interval. So we need to figure out f of 0 and f of 5 and see if 11 is between those numbers. Okay, well, f of 0 is just going to be -1 because you're zeroing out everything with an x. F of 5 takes a little more work, so that's going to be, let's see here, 25 plus 5 is 30 minus 1 is 29. And we were looking for 11. 11 does indeed fall between -1 and 29. Therefore, the IVT applies on this one. On this problem, I'm trying to show using the IVT that there is some c value on the interval from 0 to 3, some x value, such that plugging it in gives me a y value of 0, at least for this function. So to show this using IVT, first off, I need to prove that my function's continuous on the interval in question. And we can pretty easily do that. This is a polynomial. F of x is a polynomial which is known to be continuous with no proof needed. So next we move on to showing that the value we're looking for, this 0 right here, is between the beginning and ending y values for this function on this interval. So we need to figure out what f of 0 is, the beginning y value. That's going to be zeroing out everything here except the -8. So -8 is my f of 0. That's where we're starting for y values. And in order for us to show that 0 is somewhere on this function, we're hoping to get a positive number for f of 3. So f of 3, that's going to be 9 minus 18, which is, let's see here, that's -9 minus another 8 is going to be -17. Well, that's an issue. 0 is not between -8 and -17. That means the IVT does not apply to this problem. We're not guaranteed to pass through 0. We're starting negative, we're ending negative. It's possible we pass through 0, but we can't guarantee it with the IVT. On this one, we're asking if the IVT shows the existence of a c value on the interval 0 to 3, such that plugging it in gives us a y value of 4 for this function. So to guarantee anything with the IVT, we need continuity, and we've got it. This is a polynomial which is known to be continuous. So we're guaranteed that we have to go through every single y value between the starting and ending y values. We just need to make sure that the starting and ending y values, f of 0 and f of 3, basically sandwich this y value we're looking for over here, 4. So plugging 0 in then to the function, f of 0, that's just going to be -2, zeroes out all these other terms. Plugging 3 in, that's going to take a little more work. Let's see, we got 27 minus 9 is 18, plus 3 is 21, minus 2 is 19. And 4 is between -2 and 19. Since our function's continuous and we're starting at -2, ending at 19, we're guaranteed to go through 4 somewhere along the way. So the IVT guarantees that there is a c value that makes this happen. On this problem, we're asking if the IVT shows the existence of a c such that f of c equals 6 for this rational function on the interval from 0 to 2. So to use the Intermediate Value Theorem, we need to show that we have continuity for our function, at least on the interval in question. It doesn't have to be continuous everywhere, but this function needs to be continuous between 0 and 2. Well, good way to show that is to find discontinuities and show that those are outside the interval. The only discontinuity for this function is x equals 1. That gives you 0 in the denominator. But that's an issue because that infinite discontinuity at x equals 1, that is on the interval from 0 to 2. Since that shows we do not have continuity on the interval in question, that means the IVT does not apply in this problem. For this problem, we're trying to figure out if the IVT shows the existence of a c value where f of c is 6 1/3 for this function on this interval. So basically, are we guaranteed to have this y value show up for this function between the x values 2 and 4? With IVT, we always check continuity of the function on the interval. Where is this function discontinuous? Well, we have an infinite discontinuity at x equals 1. But that's actually okay, because that happens outside this interval. We know that rational functions are continuous wherever they do not have holes or asymptotes. So we're definitely continuous on the interval from 2 to 4 then. So we can keep going. That means we have to plug in the first and last x values to get the first and last y values for the function. And let's see if 6 1/3 is between those y values. So plugging 2 into my function, that's going to be, let's see, 4 plus 2 is 6. Down here we have 1, so that's 6 overall. If I plug in the x value 4, 4 squared is 16, plus 4 is 20. We're dividing that by 3, so 20/3 is 6 1/3 between 6 and 20/3. Well, 20/3, if you actually turn that into a mixed number, that's going to be 6 2/3. Well, 6 1/3 is definitely between 6 and 6 2/3. So the IVT guarantees then that we can find a C value that makes this happen.